All right, so my name is Kevin Tobias. I'm the Director of Product Management at Kratos. I look after our edge solutions, primarily around digitizers and our OpenEdge platform, which is our edge native terminal model. Today, I want to talk to you a bit about digital transformation and how it is impacting satellite. We'll use that contrast against what we see happening in the terrestrial networks today and how those benefits that we see there can be applied in satellite. We'll also talk a bit about the challenges that are seen today when deploying traditional terminals. And we'll talk about how leveraging virtualization at the far edge or the remote site to create software-defined terminal solutions can help relieve those challenges that we see in the traditional deployment of a terminal. And so what I'll do is I'll walk through a couple different scenarios that talk about adding new services and what that looks like in a virtualized approach. So we hear the word digital transformation. We hear it in the context of telco, we hear it in the context of terrestrial, MNOs, edge computing. It seems to be all over the place. So what does it actually mean and how does it apply to networks? So what we're seeing is the virtualization of network functions, NFV, is basically taking physical network functions that carry out a particular task. Typically these today are in purpose-built hardware to carry out a particular task. That might be a firewall for security, it may be routing, it may be acceleration, it may be an application that is a workload to provide insights at the edge. All of these things in the past have generally required their own purpose-built hardware, and in turn, that ends up looking like a stack of equipment that has to be essentially managed in a one-to-one relationship with each one of these network functions. Orchestrating all these things together to actually implement a service for the customer becomes quite cumbersome. And so what virtualization aims to do is we can take the physical network function, virtualize it into software, and we can run it on general purpose compute. So that's going to bring down your overall footprint. So that's going to save in CAPEX. It's going to lower your overall operational complexity of being able to manage that thing. And when we think about digital transformation in terrestrial networks today, it's table stakes to have virtual and containerized network functions at the edge. The satellite industry, however, has lagged for some time now in this digital transformation journey, but we're just beginning to see virtualization of the modems, virtualization of the network functions that are needed to carry out an end-to-end service. So today I want to talk to you a little bit about what the benefits of that is as it pertains to satellites, specifically what we would say is the far edge. So this is the remote site. It is the farthest network edge away from the core of the network. All right, so just baseline, we'll start at what does the traditional SATCOM network look like? Again, we've got a variety of network functions that are needed to carry out providing internet connectivity to an end site for whatever the particular use case is. We have in the gateway where we're connected to the backbone internet, we are channelizing, combining, we have splitters, we have combiners, we have modulators, demodulators, packet processors, all of these things that are needed to actually process the signals and carry out the packet conversion from the internet. So essentially what you see there represented with the large antenna is a gateway. You've got stacked hardware depending on how large the network is. Further, when we talk about the different network topologies and waveforms, bands, orbits, all of the different variations that you would see in a network typically are driving a different set of hardware combinations to be able to go and implement that. And then to the left, you see we have a network operations center, and this is just basically our network management system where we can go off and provision, we can maintain, we can scale, we can monitor our network. And then off to the right is really where we're going to focus today. And this is at the remote site. Everyone, we're here at Satellite, so we know when we talk about remote, I mean, it's our value proposition that we have in Satellite is we can provide ubiquitous connectivity to the hardest to reach places on the globe. And so these remote terminals are going to look different depending on the use case. If we're comms on the move, we may need an electronically steerable antenna, flat panel antenna that might go on top of an aircraft. In the case of a broadband or a trunking type solution, we may use a parabolic antenna, point that at boresight for a geo. But same thing is true here at the far edge as at the near edge. Each remote is providing a service. It's providing a solution to the end customer. And so it's not just about the satellite terminal, which is the antenna, the buck, the LMB, the modem. It's also about what else do I need to provide that service? So if it's cell backhaul, I may need acceleration. If it's a multi-orbit solution, I may need something like SD-WAN to be able to bring multiple WANs in and be able to provide a consistent QoS. These are the things that are needed at the far edge. So let's zoom in a bit and look at what a typical stack of hardware looks like. And I'll begin by telling a little bit of a story, a personal story, where in my past life in engineering, I spent time deploying a number of terminals. And as the use cases would change, I would have to go back to the terminal site and I would have to add another piece of hardware. And I would go back and I would provision it and I would configure it and begin to provide the service. And I started to notice a reoccurring theme, which was every single time I wanted to scale it, add more bandwidth, add a new service, I had to go back and revisit the site and I had to touch it. I had to actually bring the hardware, I had to procure it, I had to bring the hardware, I had to stack it, mount it, connect it, and then orchestrate it with the rest of the hardware at the end site. So that story is essentially something that represents probably anybody who's installed the terminal. Everyone understands that that's the mode. Once you have deployed a terminal out at a far edge site, at a remote site, anytime you want to add or scale that service, it's going to require that you go and touch that thing. So this shows here basically an example of a stack of hardware that you would see at a remote site to provide a service, and you've got the modem, which is taking care of the satellite access at the edge. You have acceleration, you have SD-WAN, and you have an app server. It's quite often, especially in enterprise use cases, that we don't just have one WAN or one access network. And this is so that we can have a highly reliable service for the enterprise so that we can carry out an SLA and be able to keep to that SLA. So you'll see that there's new pieces of equipment for each one of these access networks typically. And then there's also appliances like SD-WAN that are needed to actually mediate and bring all those things together. So this is what it typically looks like. So then what does it look like when we want to update the remote site? So I gave the example of you want to add more bandwidth. So at the end user site, you started by provisioning 100 megabits per second to the end user. That business has now grown and demand says, I need twice that much. Well, it looks like I've got to go to the end site. I've got to add another modem. And so when we talk through each one of these appliances, whether it's managing that thing over the air or it's adding new ones, I actually have to go to the end site. There's a term that we like to call the truck roll in satellite. Sometimes we refer to that as the helicopter ride. And essentially, this is what is required to go off and visit the end site to make a change. And whether that's because something in the service has gone down, or I want to scale it, or I want to add a new service, in any of these cases, a truck roll will cost more than the hardware often that is at the end site. So there's a reoccurring theme here that I'm trying to point out, and that is the operational cost of having to scale is often more expensive than your original business case. So that's an example. And then I gave the example of adding the second modem. So here's a classic case of adding a second modem to increase your bandwidth. Adding a new service. So today your goal may be to provide a trunking service generically to an end site Maybe in the future you want to add cell backhaul, or you want to add a 5G small cell so that you have a wireless WAN to be able to provide connectivity to a variety of IoT devices. Same story here. We have to go to the end site. We have to, in the case of cell backhaul, we may have an accelerator that we have to go and add to it. So that's what it looks like at a micro level, going to a single terminal. But what about when we want to go and scale to hundreds or thousands? This problem only becomes worse, exponentially worse, really, because we start to think about the business case must be on point at the beginning. So when we go to plan the networks, we have to think about, well, how much infrastructure do I really need there to meet the needs today and the needs of the future? And so there's a risk of overinvesting and heavily spending on CAPEX up front. There's also a risk of underinvesting, saying, well, we think it might grow to this, but we're not sure, so we don't want to spend the money now. And so we end up in a position where we haven't deployed the network functions that are needed in the near-term future, and we have to go touch the site again. And as I mentioned earlier, sending a tech is very costly, and scaling can take too long. Another point about deploying new services and visiting the end site, it's not just about the procurement lifecycle of actually getting the equipment to the user. It's about the user actually being able to get to the end site. So if we talk about mobility type situations, you have to wait for the ship to come back to port. If you're talking about a ski town in the middle of the mountains, you might have to wait until that 3 feet of snow that just dropped in Colorado melts down so that the installer can actually get there. So by the time the need that has been presented to the operator is met, it could be too late to actually go and address and provide a solution. So the better way, let's talk about that. We've introduced the industry's first software-defined SATCOM platform. We call this OpenSpace, and it's really aimed at exactly what I just talked about, and that is digital transformation of the satellite network, converging that with the terrestrial network and being able to orchestrate it. So let me walk through how that happens. The first step, you guys are probably all hearing the term Diffie, right? This is taking the RF signals at L-band from the antenna and converting them into a standard IP packet at the antenna. These digital IF packets are then sent to containerized or virtual network functions that take care of the digital signal processing. So what would have typically been done on a hardware modem, those elements, the modulator, the demodulator, those can be virtualized and run on general purpose compute, which means we can scale to a variety of different locations, whether that be in the cloud, on premise, or even out at the edge. And once we've virtualized, we can begin to string together these containerized network functions into service chains. And so what that means is it's not just I can now spin that one thing up, it's what are the common things that I put together to deliver a service, and now I can spin that up as a service chain. So if it's cell backhaul, if it's an enterprise extension, once I've gone off and put that service chain together for my customer and I've deployed it one time, I now have a catalog where I can say I want to go deploy that continuously, and I can allow my telco customer to be able to go off and send a common command. My colleague Marcus in 2 hours will be talking about MEF 3.0 and E-line, carrier Ethernet. This becomes extremely important in this part of the conversation, so I won't steal his thunder, but essentially you allow the end customer to deploy network services the same way, in a common way that they would, whether it's over a terrestrial microwave link, fiber link, or over satellite. This begins to bring us into a place where we can orchestrate all of those. So, and at the end of the day, when you have those, now you have a way to automate your service delivery. And ultimately, we talked about the lag in time from when I understand that I have a need at my end customer's site to when I actually want to deliver it. This automation allows us to quickly address that need, which is going to give us the ability to scale the networks faster and ultimately recognize revenue faster. So let's talk about what this looks like at scale. When we apply this network function virtualization, simply it's taking those things that we talked about that are built on purpose-built hardware, channelizers, combiners, modulators, demodulators, virtualizing those, and running them in the points of presence that make most sense for each one of those use cases. You get a lot of diversity when you're able to move around in the cloud, public, private cloud, on-premise. And then when we zoom in on the right side of this, we can apply the open space principles and technology to the far edge and be able to benefit from everything that we see in that cloud native environment on the gateway side. And so what you see here is moving away from the stack of equipment and taking those network functions, virtualizing them, and running them on general purpose compute. We take the same step, we digitize into a standard packet, we send that to the general purpose compute where we can actually process that. So let's zoom in on the practical examples that we talked through earlier, what it typically looks like to deploy a terminal and kind of how does that differ when we're in a software-defined use case here. And so basically what you see is the representation of those network functions virtualized here. So we have our modem, the modulator, demodulator, encapsulator all running in a CNF. You have an SD-WAN. You have acceleration. And one of the key features of being open and being virtualized is when we disaggregate that network function from the proprietary hardware, we open up choice. We open up an ecosystem. So as long as you're meeting the runtime requirements of that compute, you're able to go and pick the vendor that makes the most sense to you. So when you talk about SD-WAN, do a quick Google search, you'll find there's 12 vendors right away. You can go look at Gartner's Magic Quadrant and you can see how they all line up. What is the value that each one of them bring? For every customer, you're gonna have a unique set of needs, and disaggregation allows you to go off and choose those because you're running on general purpose compute. So you can tailor the terminal to your particular use case. So it's an ecosystem of many vendors, which is going to prevent that vendor lock-in that you see, where when you want to go and scale, you have to continue to buy from a single vendor. This gives you that choice. So what does it look like to update a software-defined terminal? And again, when we talk about a software-defined terminal, we're really talking about the edge holistically. So we're thinking about how do I manage now these multiple network functions that I need to meet my service and be able to update those as an orchestratable service chain, and not just I need to log into each one of these machines that are behind the modem and update them through their particular update cycle. We can begin to orchestrate that. We can begin to think about how to actually provision new services as well. And so I think one of the common use cases that we're hearing now in this multi-orbit world is the ability to add multiple modems and be able to bond those together, ultimately to be able to provide more throughput. Sometimes that may be because we have limited bandwidth available, so we take multiple carriers from one operator. It could also be that we take carrier from a GEO and from a MEO or a LEO, and we bring those things together. When we actually have the need, we can wait until we actually see the business case evolve. So if today I'm okay with 100 megabits per second with a single modem, and I don't see any scaling happen, I don't need to go and over provision and add another hardware modem until I actually need it. And what this provisioning looks like in a software world is, again, deploying over the air and spinning up this new modem on that common edge platform. And so what that ends up doing is it prevents having to send an installer out to the end site to go stack that extra piece of equipment. It's just going to decrease your time in being able to respond to the business need on the ground. So that's one practical example of how do I add more bandwidth. Additionally, what if I want to add another service in this case? The same principles apply here. So I can go look at what is the service that I am looking to provide to my customer. I can go into the ecosystem of applications, say in a cell backhaul example, maybe I want to pick a zip link. I can go and grab that application from the vendor. I can license that and I can provision it over the air at the far edge site and not have to go visit the end site. Many stories about wanting to scale that end site because we didn't know that there was going to be that much demand, or maybe something like a natural disaster happens at the end site. We'd be able to actually scale the end site and provide the additional connectivity and bandwidth to the end customer quickly, which is crucial in time-critical use cases like that. So what does this look like scaling on demand when we move to a software-defined mode? Just to rehash, it's less risk of over and under investing. We're able to do it in software, so at a moment's notice, bring up what we need. Scale elastically. This is important as well. When we virtualize, say, a modem, for instance, we have different sizes of modems, we have different waveforms, a variety of different products. Being able to simply scale beyond what my original use case was. Often you get tapped out when we're in a hardware implementation because we say this is how much I can support. When we have compute that's running at the edge, we can look at elastically increasing the size of that modem to increase the overall bandwidth. So this helps us to capture that new business quickly while it's relevant. And then orchestrating the edge services, as I mentioned previously, this allows us to service chain together virtual network functions, be able to deploy them over the air in a repeatable way where I don't have the opportunity to mess up with the installation, connecting cables. It's a repeatable software-defined approach. The future-proofing sites for new technology is another important aspect. I think if everyone here was talking and had to make a guess about what is going to be the winning waveform in 5 years, you'd have a lot of different answers, right? People would be talking about 5G NTN, they'd be talking about 6G, they'd be talking about S2X, proprietary waveforms. You can take the guesswork out of what is going to be the next technology that I need to adopt when you're in a software-defined world. This gives us the potential to not have to go to the end site to pull out that hardware, to put in new hardware for that next set of capabilities. And then again, it's sending the installer once and then relying on zero-touch provisioning to maintain and grow the end site. So to rehash the benefits, this just kind of shows at full scale what a software-defined terminal could look like in an enterprise with different use cases. We can cater the general purpose compute to the use case. We can spin up the applications that we may need to provide the service. We can pick from the ecosystem and avoid vendor lock-in, and that's going to allow us to scale on demand, accelerate our time to revenue, enable orchestrated operations, and provide zero-touch provisioning. So many of you may hear this and say, oh, that's a nice slide deck, Kevin. It sounds very interesting, sounds very promising, but is it real? And it is. We have this today. We have this deployed today. We'd like to invite you to come by our meeting room in 150 to take a look at a couple different use cases. And so I'll just highlight them real quickly here. What we're showing in our meeting room are live demos with a virtualized gateway, which we call a vStar, running DVB-S2X. We have 3 different OpenEdge terminals that take this software-defined principle and apply it to the far edge and to the remote terminal. We're running a variety of different applications and modems. In one use case, we're running MEF 3.0 carrier Ethernet extension over the top with this edge. In one use case, we have a zip-link accelerator for cell backhaul in combination with a virtual modem. And then very interestingly, for the trunking use cases that I talked about where we have multiple modems, we have a multi-carrier trunking terminal where we actually have 3 modems that are running on a single edge and then are being bonded together to deliver an end trunk service. We also, with the SD-WAN, take a terrestrial connection and include that with the non-terrestrial connection and bond those together just to show a variety of different use cases that could be deployed at the edge. So we invite you to come by our meeting room. There's a QR code up here on the screen. There is a demo, live demo at 2 o'clock that you can drop in by room 150. If you're not able to make that time and you're interested in learning more about the technology or getting a demo, please scan the QR code and you can make an appointment through that. So with that, I thank you for your time. I appreciate you and hope you enjoy the rest of the show.